Today I'm talking about lower bound methods in quantum chemistry. I'm going to talk about two different approaches that are actually the same approach, variational two-electron reduced density matrix method and the sum of squares approach. And the sum of squares part of this is collaboration with Nick Rubin, who's sitting right here and is giving a talk tomorrow. Okay, so as an outline, like I just said, I'm going to talk first about a problem in quantum chemistry that's variational optimization of the two-electron reduced density matrix, or the 2-RDM. And then I'll connect that to the sum of squares decomposition of the electronic Hamiltonian. And then I'll try to connect the two. And if there's time, I'm going to talk a little bit about ensemble versus pure state N-representability. But I don't know if you guys will be too tired or if we'll be out of time. So the motivation for using a method like the variational 2-RDM approach is that doing quantum chemistry exactly is exponentially complex. And so as an example, we can choose a method, a standard method in electronic structure that's called complete active space self-consistent field method. This is an approach that can give you a qualitative picture of difficult processes like bond-breaking processes in quantum chemistry. And it's based on, I think I'll say in a moment, it's based on configuration interaction. So this is an example of a dissociation of a molecular nitrogen. I'm breaking 3 bonds here. And to describe this curve correctly, you need to include at least the 6 electrons that are involved in those 3 bonds. And in CAS-SEF, what you do is partition your molecular orbital space into regions that are not important for the chemistry that's happening and are doubly occupied or empty, and then where all of the action happens. We call this the active space. And the way you write down a wave function here is you write down every possible way of distributing these 6 electrons amongst these 6 orbitals, and then put parameters in front of them and wiggle the parameters to minimize the total energy for the system. And this type of approach is great. It gives you a qualitatively correct picture of complex processes like this. The problem with such an approach is that you run out of steam very quickly when you go to larger systems. So the number of variables in this type of a wave function will blow up combinatorially with system size. And so at about 22 electrons and 22 orbitals, you can't do this type of calculation anymore. So if you want to go past this limit, you have to find some other representation of the electronic structure that scales polynomially with system size. And the approach I'm going to talk about in the first half of this talk is this variational 2-RDM approach. And there's many other ways to do this. So there's approximate CIs, selected CI or heat bath CI, tensor network methods, and so forth. But I'm going to focus on the 2-RDM methods. OK, we can get away with using this 2-RDM instead of a wave function because the energy is an exact functional of the 2-electron reduced density matrix and the 1-electron reduced density matrix. And in terms of the other parameters here, this small h is we call the core Hamiltonian. This is like the kinetic energy of your electrons and also electron nuclear attraction, so the external potential they live in. And then this other term is the electron-electron repulsion term. And physically, these quantities map onto density distributions. So the 1-RDM maps onto a probability distribution, where will you find your electrons? And then the 2-RDM maps onto a pair probability distribution, where you say, OK, I have got an electron that's sitting wherever this E is, where am I likely to find the other electron? And you can see that these electrons' motion are correlated. And the cool thing is that just with information about these probability distributions, you know the energy exactly. And so since the 50s, it's been very tempting to try to develop a variational procedure where you determine the elements of these density matrices directly without knowledge of a wave function by varying them. And that's a great idea because these are nice compact objects, much more compact than the wave function, but it turns out it's actually a terrible idea because if you're not careful, you'll get trash for your results. And there's my animation again. OK. So it turns out you need to impose many, many conditions on these density matrices to make sure that they derive from wave functions. If you were here last week, Paul gave a great introduction to the N-representability problem. I'm going to cast things, I'm going to describe things in a slightly different way today. So here's the formal definition of an ensemble N-representable 2-particle matrix. It's obtainable by integrating out all but 2 electrons from a sum of N-electron density matrices, where these weights are non-negative. So this is an ensemble of density matrices. I've integrated out all but 2 electrons. This is great definition, but it's useless in practice because it requires knowledge of the wave function. So instead, we try to think of necessary conditions for ensemble N-representability, and we enforce those on the RDM. So first, This quantity needs to be Hermitian. It needs to have a fixed trace, which fixes the number of pairs of particles in the system. We're dealing with fermions, so it needs to be antisymmetric with respect to the exchange of these labels in the top and the bottom. And then the least trivial constraint to impose is that the eigenvalues are related to probability densities, so they need to be non-negative. So at the end of the day, this ends up becoming a semi-definite optimization problem. And there's lots of people in this room that have written down procedures like Sten or Paul, Nick, to optimize the 2-RDM directly like this. Okay, so in practice, what does this look like? Here I have a silly small molecule and a very small basis set, and this is the full CI. This is the exact answer in this basis set. And if I carry out an optimization with the constraints on the previous slide with imposing non-negativity of the eigenvalues of this density, then what I get is trash. I see that the energy is way too low, which immediately tells you that this density matrix is not N-representable because it's violating the variation theorem. I can't get an energy lower than the full CI energy. And then the shape of the curve is wrong. Everything's wrong. So we're missing something, and that something is additional N-representability constraints. And you can cook them up by thinking about other types of pair probability densities and making sure that these, or higher combinations of particles densities, and make those positive as well. So instead of thinking about the joint probability of finding 2 electrons, you could think about finding 2 holes or not finding 2 electrons. And if you keep this matrix positive as well, then you find at least the curve is bound, but the energy is still completely wrong. You could think about a particle hole density matrix, and now you get something that looks qualitatively correct, but the dissociation limit is still wrong. And I'll come back to this point a little bit later. These conditions on these 3 density matrices have been known for a very long time, since the 60s. These are called the PQ and G conditions of Garrett and Purkis. And one of the nice things about RDM theory is that types of conditions like this live in a hierarchy that's systematically improvable. And you can generate these conditions in the way that Paul was describing last week by thinking about different Hamiltonians that you could construct from different types of operators. Or you can cook them up in this much simpler metric, to me, much simpler because I understand it, metric matrix picture. So basically, if I have my wave function and I define some basis function as the action of this operator on that wave function, and then I can construct an overlap matrix from these basis functions, and by construction, this matrix should be non-negative. And so depending on how I choose this C, I can cook up different classes of N-representability conditions. So I could start with just the 1 particle level, where I could build elements of the 1 particle reduced density matrix or the 1 hole reduced density matrix, and this tells me that these 2 matrices need to be non-negative. And not only should they be non-negative, but they should be related to each other in this way, and this expression is implied by the algebra of the operators that define these matrix elements. Make sense? Yeah, super simple. Okay, so that's the 1 particle level, and if you have an algorithm that depends on these conditions, then you can solve for the electronic structure in power 4 time. And so this is something like Hartree-Fock theory you could write down in this way. At the 2 particle level, there's these 3 matrices that I already mentioned, the D, Q, and G conditions. And if we impose these conditions, we can cook up an algorithm that now scales as the 6-power system size. So that's getting more expensive, but it's still very manageable for electronic structure, from an electronic structure point of view. You could go beyond the 2 particle level and think about 3 particle conditions. So here I've enumerated 4 different conditions. Imposing these we call 3 positivity. This would give you a result that's exact for a 3 electron system. Imposing these conditions is very expensive. It's 9th power system size. So we also have partial 3 particle conditions that we call T1 and T2 that you can get from linear combinations of these 3 particle matrices. Okay? So we have this hierarchy of conditions, and if we go up to the n particle density matrix, then we have an exact theory. It's just like the full CI, full configuration interaction, but it's as useless as the full. It's probably more useless than the full CI because you're never going to be able to solve this problem computationally. So we usually stop at the 2 or 3 particle level, and then you can devise an algorithm that scales polynomially with system size. Okay, so here's the chemistry. There's like 3 slides that you can bear with me for, and then I'll put up more equations that will make everyone happy. Okay, so if you have one of these algorithms, you can start to ask questions about electronic structure that you might not be able to ask otherwise. And so one classic problem that people in my community think about when they're thinking about what's called strong electron correlation is the emergence of polyradical character in molecules that look like this. These are carbon atoms. Each of these vertices represent carbon atoms. And as these chains get longer, you get more and more open shell character, more and more unpaired electrons, even though the ground state is a singlet where all the electrons should be paired. So we have a few different measures of electron correlation that we can pull out from one of these calculations. So one is based on natural orbital occupation numbers. This is the probability that an orbital is occupied or not. So 2 means it's a doubly occupied orbital. 0 means it's empty. And so for small members of the series, you see the orbitals are basically doubly occupied or empty. So this is like a molecular orbital theory type picture. But as you go to larger members of the series, then you start to see density leak out of the highest occupied natural orbital and into the lowest unoccupied natural orbital. And then we have 2 orbitals that are both singly occupied here. So this is a singlet biradical. And they get even more complicated polyradical behavior beyond that. If you go to these quasi-two-dimensional acene molecules, you start to see the same thing, but this polyradical character emerges much more quickly. So in the case of the circumacenes, it's kind of similar to this case, but these periacenes, you have already singlet biradical character when you get only to 5 fused rings in this direction. So from this point of view, this is a much more has much more polyradical character. It might be much more unstable chemically. Okay. One thing to point out here is that this calculation corresponds to a 64-64 active space. If you remember my slide from earlier on, that'd be like a the equivalent of a wave function with like 10 to the 50 variables in it or something like that. It would be an impossible calculation to do from an exact configuration interaction point of view. And with a good SDP solver and a good GPU, you can do this, and taking advantage of various symmetries, you can do this calculation in something like 4 hours. That's pretty neat. Let's see. You could have this other way of measuring unpaired electrons. We have this quantity called effectively unpaired electrons, and you see that they build up at the edges of the molecules. And if you sum up the numbers that correspond to these circles, you can count how many electrons live at the edges, and it turns out there's more of these unpaired electrons in the periacene molecules. So that's consistent with what we saw on the previous slide. And then there's geometric indicators for this polyradical character as well. But I know that you guys don't care about this, so I'll skip that. The point is the periacenes have the most polyradical character. So that's awesome. So we can do these really big electronic structure calculations. Everyone should stop doing RDMFT and any other method and use these 2-RDM methods, right? Is that right, Nick? Should we all stop and focus on 2-RDM theory? Probably not, because these methods actually have some really serious problems associated with them, and some of them maybe someone in this room knows how to solve them, I don't. So problems. One is related to that dissociation limit that I mentioned a while ago. Here I have this is a slightly different basis than I had before, and better colors, I guess. And you see that with CI and 3-particle conditions, I get a great dissociation limit, but the dissociation limit is wrong if I limit myself to 2-particle conditions. Why is this dissociation limit wrong? Well, we can get some indication of that if we think about relaxing some of the constraints that are involved in this calculation. So for example, in this calculation, I've constrained that I have a chalkboard. I've constrained that the expectation value of the spin squared operator is correct. And I've constrained that the expectation value of the projection of spin operator has some value. And then I've also constrained that the variance on the S squared operator is 0. If I lift these constraints, then I see that the answer is worse in both cases, the PQG and PQG T2 case. And now the dissociation limit is wrong, even with 3-particle conditions. That seems quite bad, because this is a really expensive calculation. This is happening because, as Paul and others pointed out more than a decade ago, 15 years ago, the V2RDM methods have this problem that's very similar to something that's happens in DFT, and that's that they lack what's known, it's a derivative discontinuity problem if you think about systems of fractional numbers of electrons. So if you had an ensemble of wave functions that described some fractional number of electrons, you should be able to connect these points at integer values of the number of electrons by straight lines. But you see, you don't get a straight line when you do the 2-RDM methods. You get these curved lines, and now the minimum in this might not be at an integer value number of electrons. So that implies that fractionally charged atoms are sometimes preferable within this framework. And if you go back here, we're dissociating into two different fragments, and they should have integer numbers of electrons on them, but they may not, because that might be energetically favorable in these methods. It's very similar to the same problem happens in density functional theory. Second problem is that, as I described this to you, in the quantum chemistry community, a ground state method is nice, but what you really want is to be able to describe ground-end excited states. And that CAS-SCF approach I mentioned is generalizable to ground-end excited states, but this V2RDM approach is not. It's a state-specific theory. The only way you can get at any kind of excited states is if you have some symmetry that you could constrain, like the spin quantum number that I mentioned a moment ago. And so there's examples, again, from more than a decade ago from Paul Ayers and others, doing this in the literature. So spin angular momentum, I could get, if I had a two-electron system, I could get at a singlet or a triplet state, basically, based on spin angular momentum constraints. You can generalize this idea also to orbital angular momentum constraints, where you have the same type of idea. But this is a much more limited scenario because these L-squared constraints are only relevant for atoms, and the LZ constraints are only relevant for atoms or linear molecules. And then you could generalize this to the total angular momentum case, where J is the sum of spin and orbital angular momentum. But again, it's only relevant for atoms or linear molecules. So this is basically the only way to get at excited states that I know of in this context of these theories. OK, let's say that I'm doing some kind of calculation involving total angular momentum constraints. If I have a non-relativistic Hamiltonian, OK, I'll put this up. If I have a so I have a carbon atom in a bunch of triplet p states, and I can have different ways of coupling the orbital and spin angular momentum for this term. And I could have total angular momentum equals to 0, 1, or 2, and then for each of these, I could have different z projections of the total angular momentum. And if my Hamiltonian's not relativistic, these should all be degenerate, and they're clearly not. So you can see the higher, so this is given as error in units of millihartree. And so as you go to the higher J values, you get better constrained RDMs and better energies. And in each case, in any manifold of M sub J states, you see that you get the worst behavior for the the spin projections in the middle, and you get the best energies for the maximal spin projections. So, yeah. Sure. Do you want me to say all the words over again?
No,
I'm just kidding. Differently. Okay.
What do you mean by degenerated?
So if I have a system with j equals 1, there's only one option for m sub j. I would also have m sub j equals 0. If I have j equals 1, I could have m sub j equals 0 or plus or minus 1. If the Hamiltonian doesn't, et cetera, if the Hamiltonian doesn't include spin orbit coupling terms, the states represented here should all have the same energies. And so what I'm measuring here is the error in the energy of the state relative to full CI. And you can see that the errors are different for the different m sub j states. That means these are not, they're not degenerate. They don't have the same total energies, but they should. So we did this in the context, we were trying to develop a relativistic version of these methods. And we look at these data and we're like, this is completely hopeless because you can't describe the non-relativistic limit correctly. Did I answer your question? Enough? OK. All right. Don't ask questions because everything I know is on the slides. There's no more information in here.
OK, then I ask a question. This has to do with the SU2 representations? Representation of the unitary group of two.
Help me, Nick. Yes. Nick says yes.
Yes. So that gives it at least a math link, right, where these numbers come from.
Yes. Thumbs up. OK. OK. So this problem is generalizable to other types of states. This is a general problem here. We'll skip that.
Eugene?
Yes.
Is that because there's less variational space in the maximum projected states?
I actually honestly don't understand why this happens. I think that in Paul's paper, you guys have more strict pure state constraints for the
We did the
maximal ones. But
effectively for J plus of the state equals 0.
Okay,
right? That forces you to be an eigenstate.
for the maximal projection.
For the maximum projection, you can't do it in the middle.
But that's still an expectation value constraint, so I don't think it...
No, even hard.
Okay.
Even with Lagrange multiplier.
So what on the maximal one, on the highest J state, you could apply a raising operator and enforce that that gives you 0. But you can't do that in the middle, that's the point.
Is there a way to like apply like Wigner-Eklas theorems there?
I think they derived conditions based on this, but they're not as strong. Okay. Okay. I got confused because I thought there were more slides before this part. But now this is the transition to the sum of squares representation. Wow, this is going to be a very short talk.
I'm slower.
Go slower? Okay. Sum of squares. This, I was only introduced to sum of squares like a year ago. You guys all probably know what this is. It turns out that this V2RDM problem is very closely related to this sum of squares problem. And so I'm going to walk you through what sum of squares looks like just from the point of view of this, decomposing this Hamiltonian and then connect it to the V2RDM problem. So let's imagine I have a Hamiltonian that has a one-body piece and a two-body piece. This is just like the chemistry Hamiltonian that I was dealing with before. And I want to define a sum of squares Hamiltonian that has this form. It's HSOS. It looks like a sum of squares of operators. And I want to define this Hamiltonian such that it gives me a one-body piece, a two-body piece, and a constant. And I want to find these operators such that I have equivalencies between the one-body piece and the two-body piece. That's it. And now, if I take the expectation value with respect to whatever the lowest energy eigenfunction is of this Hamiltonian, then I see I have my sum of squares expectation value gives me back expectation value of h, because I've made sure these operators are equivalent, plus now this constant. And this expectation value should give me my ground state energy. And lambda is just another constant. And by construction, this operator should be, the spectrum should be non-negative because it's a sum of squares of operators. So this sum has to be greater than or equal to 0. This implies that the energy is bounded from below by this, the other way around. This energy is an upper bound to the negative of this constant. So in this sum of squares representation, this lambda is related to the ground state of the Hamiltonian, ground state energy of the Hamiltonian.
So you made a comment that you want your one particle Hamiltonian to be equal to this particle Hamiltonian, but it's the same, right? And it's same on both sides.
Yes, so if I want the H1 to be equal to H1 SOS and H2 to be equal to H2 SOS. So basically I have a whole bunch of operators here with different coefficients in them, and I bring them all to the same, a common order as what's used up here, if that's normal order with respect to some vacuum. And then I equate the coefficients in front of the terms. Okay? Okay, so I'd always known that the energy in V2RDM was a lower bound to the true energy, but I never really saw it from this SOS point of view. Once I show you this is the same problem as V2RDM, it's very clear that the energy should be a lower bound to the true energy. Okay, so this procedure gives you a rigorous lower bound to the ground state energy. Should I go slower? Yeah, I'm so sure I should give it 3 bars. This is math. You guys are math people, sorry. Okay, yes, so now I'm calling this ESOS is equal to E lambda. Okay, so how does this work? Here's a very simple quadratic example. I've got a Hamiltonian that has only 2 operators. And I want to write down the SOS version of this operator and find out what the ground state is. So this is the form. I want to have an operator that's squared that's related to mode 0, and an operator that's squared that's related to mode 1, and I need to figure out what these operators should be. The generators for these operators should be linear in the creation annihilation operator, so they should look like annihilators or creators. And then you take Hermitian products of them, and you get the things we're looking for. And it's not too difficult to see if I choose O0 to be A0 and O1 to be A1 dagger, then I get a Hamiltonian that looks like this, and then I use my anti-commutation relations for these operators, and now I have something that looks exactly like my original Hamiltonian plus a constant. So this tells me the SOS energy is equal to -1. So the ground state energy of this Hamiltonian is -1. In this case, this isn't a lower bound. It is exactly the energy, the ground state energy for the Hamiltonian, because I have an algebra that is complete. In the quadratic quartic case, things get much more complicated because now I have one-body operators and two-body operators. And so the generators need to be at least quadratic so I can generate things that look quartic. I say at least because I could have as many operators as I want as long as when I evaluate the sum of the squares of them, I end up with only one and two-body operators. So that should remind you of the T1 and T2 conditions I mentioned a while ago. I should have mentioned those don't actually involve three-particle operators. Okay, so here the minimum suitable algebra will be SOS k equals 2, and that set of operators should span all of these two-body operators. So I have generators that these look similar to the generators for the N-representability conditions at the two-particle level. This one would give me the P condition involving D2. I think I have it the next click. So this guy should give me something that looks like D2. This guy should give me something that looks like Q2. This guy should give me something that looks like G. But now I have this other one that is like the whole version, the whole particle version of this guy. And so this algebra is actually more complete than it was in the other version of this problem. And so now my G matrix is actually a lot bigger than it would have been in the original problem. In the V2RDM problem, I only have this piece to worry about. But in this version of the problem, now this is one piece of a 2x2 block matrix.
Are you saying that the exact Hamiltonian will be recovered with those operators, or that this is an approximation?
No, I will get back exactly the right Hamiltonian. That is because that procedure gives me back coefficients that recover the exact Hamiltonian. But the shift will not be exact until this set of operators is complete.
Right, so you might need three-body and four-body.
Or more, yes, exactly. So this is the minimum algebra that you could work with because you need to recover an operator like this. And actually, I'll show you in a few slides that you can use a very slimmed down, dirty version of this. This is the true minimum. But really, you need some two-particle operators. OK, so then the procedure to obtain the SOS Hamiltonian is I want to maximize this SOS energy, which is negative lambda, such that those one and two body pieces of the Hamiltonian are equal to each other, and also that each of these coefficient matrices is positive semi-definite. And remember, this one is bigger than it was in the other version of the problem. And you can at least qualitatively argue why it should be bigger than in the other version of the, or at least rationalize why it's bigger. When you want to bring all of your operators to a common order to be able to equate the coefficients, and this term gives you a constant that helps you maximize your objective function. So this piece is important in the dual representation of the problem, in this SOS representation. OK, so now, a numerical example. I have my same silly molecule, CI. This is V2RDM with two-body conditions. So this curve looks the same as before, but the colors are different again. And I have changed the volume for some reason. OK, so now I do my sum of squares calculation, and I get results that look pretty similar to the V2RDM calculation, but they're not quite the same. So this energy is a lower bound to the V2RDM energy. Any ideas why? Yeah, neither of them would give you N-representable RDMs. Symmetry constraints. So there's a whole bunch of constraints that were in my V2RDM problem that aren't in the SOS problem. The SOS problem knows nothing about particle number. It knows nothing about spin symmetry. It knows nothing about any of these symmetries that are in the V2RDM problem. It just knows the Hamiltonian. But by some miracle, this gives you a very good approximation to the V2RDM energy, just based on only the algebra. It's very cool. So that's why there's such a big difference between these two guys. OK, so now, if I remove at least the spin symmetry constraints from the V2RDM calculation, then I see much better agreement between these two approaches. But they're still not quite the same. The SOS energy still is lower bound to the V2RDM energy because there's still particle number constraints. And it's also much easier to enforce anti-symmetry properties in the V2RDM problem than it is to enforce the same properties in the SOS problem. So anyway, they're close to each other. There are certain limits where you can make them look exactly the same. but not in this case.
But is it always true that the V2 RDM is larger? Gives you a real example?
I think it should be because there's always additional constraints in the V2 RDM calculation, like the particle number constraints, for example.
Okay. I didn't know that.
How do the particle numbers enter into the SOS?
They don't. So if you have a Hamiltonian that's ground state has a fractional charge for some reason, the SOS would pick up that ground state. It knows nothing about the particle number. It will find a lower bound to whatever the ground state of the Hamiltonian is anywhere in any Fox space sector.
Sorry, two questions. Do you have any guarantee that as you increase the degree of the polynomials you're doing, you're considering you'll converge to the right curve?
Yes. Will you say that in your talk tomorrow? Yes. Nick will talk about this tomorrow, but yes. In general, as you make the set of operators more complete, you should approach the correct ground state.
And a related question. So, for instance, if you do similar things for, let's say, combinatorial optimization, or let's say find the ground state of easy models, there are these rounding techniques that allow you to construct one, let's say, a feasible point of the original problem, form the solution of this STP. So, which probably will give you then an upper bound on the ground state energy, and this doesn't perform too poorly. Can you also somehow get a guess of some wave function that performs reasonably well from your solution?
So I could get a guess for the primal form of the problem, but anytime, let's see, but I won't know what the correct Lagrange multipliers are, so that I don't think I would see any, numerically, I don't think I would see any benefit to starting with a good guess.
No, sorry, I meant like from the solution of the SOS, can you guess like a good ansatz for the wave function?
Oh, for the wave function? No, I don't know how to extract any information about the wave function. Okay. But as I'll show you, I'm going to change your question so that I can answer it. If your question was, can I extract something from the primal form of the problem to be able to do this SOS? Yes, you can. Okay, so there, this is exactly what that is. How can I get out the sum of squares Hamiltonian from the dual of the V2 RDM problem? So this is where I am not a mathematician, so I tried. I'm going to try my best to outline these algorithms in a way that you will not get mad at me. So the primal form of the V2 RDM problem, which is what I started talking about, is I want to minimize the trace of some Hamiltonian against my solution vector. And this Hamiltonian just contains my 1 and 2 electron integrals. And my solution vector is this block diagonal, not vector. My solution is this block diagonal matrix that contains different density matrices. One-body density matrices, two-body density matrices. And now I have intentionally blown up, I have not blown up, I've added 1 to the algebra here because it makes things a lot easier. So now this G matrix looks like the original G I had before plus a 1, and then you can show very easily that there's these slices along the top row and the first column that look like the one-body density matrices. Okay, so this is my primal solution space. I want to trace this against the Hamiltonian such that a whole bunch of linear constraints are satisfied. These linear constraints are going to be things like these spin constraints or mapping conditions between different density matrices, like how D1 and Q1 should be related to each other, trace constraints, and so forth. And then also this solution needs to be positive semi-definite. So I can write down a Lagrangian for this problem, where now y are the Lagrange multipliers for the linear constraints, and this b is a Lagrange multiplier for the positive semi-definite constraint. And then if I have this 1 in my algebra, then I can push all of the constraints onto this part of the solution vector. And then I can write all the constraints such that these b's are all 0, except for the one that says this piece has to be equal to 1. So I have only one non-zero b. That simplifies my Lagrangian. And then if you notice that some of these terms look similar, you can clump a whole bunch of them together. So you have the trace of this thing that looks like a Hamiltonian minus some other Hamiltonian traced against x plus this constant y. That's my Lagrangian. So if I take that, I can define a dual function where I minimize over all of the primal variables. And you can notice that this is not going to be bounded from below. I'll get minus infinity unless this quantity is equal to 0. So now I have H is equal to B plus this sum of constraint matrices times Lagrange multipliers. And this is just the dual problem, the dual constraint in the V2RDM SDP that we solved numerically. So if I run my little calculation, I can pull out these B's and Y's at the end. And I can construct a Hamiltonian in this way. So now my question is this the SOS Hamiltonian? Is it the same thing? It might be. Let's find out. OK, so can we extract this SOS from the dual constraint? So I need to think about how I can turn these matrices back into operators to give me this SOS Hamiltonian. And I have this question mark here because this thing might not have a sum of squares structure. I don't know yet. So the operator B is already a sum of squares, has sum of squares form. It looks like these are the different pieces. And actually, this is written in a dumb way. It doesn't matter. Let's just pretend this is correct. Sure, it looks great. All of these matrices are positive semi-definite. So this B is sum of squares. So now what about these constraint matrices multiplied by the Lagrange multipliers? If you think about what each of these constraints refers to physically, you can cook up an operator form of them. So for example, if I want to say the trace, I've got a chalkboard. If I want to say the trace of my two-body density matrix is equal to n minus 1, which is the normalization we use, then I have an operator that plucks out the diagonals of the 2RDM, and then I have my constant. And then I could have mapping constraints where I want D1 and Q1 to map to each other. So they just look like the fermionic anti-commutation relations, et cetera. You could have more of these algebraic constraints relating different operators. OK, so is this thing sum of squares? OK, quadratic example. Let's say I have a Hamiltonian that's just this quadratic guy. I have my primal form of the problem that's the same as before. I have 3 blocks in my X. I have only 1 non-zero block in the Hamiltonian. And I want to do this optimization. I have these constraints where D and Q matrices need to be related to each other. And also the trace of the 1RDM needs to be correct. So this plucks out the diagonals of the 1RDM. The fun things here are some of these constraints are purely algebraic. And they will be satisfied for any state. And if you just think about what the matrix representation of these operators would be, it's going to be 0. So if I take the expectation value of this operator, it's going to be 0 for any state. So we're going to ignore all of them where I is not equal to j. And we're going to do that because the constant is very important. So we're only going to think about the constraints that will involve the constant. So that's in general true. We only need to account for constraints that involve the constant or that are not 0 based solely on properties of the algebra. So if a constraint involved the particle number, for example, we would want to include that one in our SOS as well. OK, did I miss something there? I don't think so. OK, so now I have my SOS Hamiltonian is this B, and I have a constraint for my trace, and I have a sum of constraints relating the diagonal elements of. So that's saying that D1II plus Q1II is equal to 1. OK, so I have the B's are SOS already. And I can write down everything together. So I have my B's. I have the contributions from my constraints. I can group terms. So I have a whole bunch of constants. I have a whole bunch of terms in front of my 1RDM type operator. I have some terms in front of my 1 whole RDM type operator. And now I just need to ask, are these total coefficient matrices here, are they positive semi-definite? It turns out, numerically, at least for the problems I've played around with, these guys end up being negative. And that's OK, because I can always just move this negative definite part of the operator to the other space by using fermionic anti-commutation relations. So I could always take ytr times a dagger j and just write it as delta ij minus ji dagger. And I could do the same trick here. So you're just trading pieces back and forth. And now I have, I pick up additional constants. And now I have a term that is positive semi-definite, another term that's positive semi-definite. So now this thing is SOS. So this is my SOS Hamiltonian extracted from the dual of the V2RDM problem. That's fun. What's even more fun? What's even more fun is I guess I was missing operators. I don't know what this is. Oh, yeah, I changed equations. This is the correct equation. Doesn't matter. What's fun is this part, constant part, is equal to the negative of the primal energy. Now we're done with the quadratic part. So this actually gives me a check to make sure that I've constructed this correctly. My constants should sum up to the negative of my primal energy. OK, how are we doing on time? Oh, man. OK. I went slower. Hamiltonian for interacting electrons is quartic. And now the resulting algebra can become extremely messy. So do you want to go through all of that together in great detail?
No, but I want to
Oh, you want to ask me?
make a suggestion. So I have a colleague, Bill Helton,
Yeah.
worked on matrix valued sum of squares a decade with his collaborators. And it just looks that maybe one can import some of his tricks, or at least it's worth looking.
Yes.
Because he somehow works with larger matrices, writes them of sum of squares up there, and then goes back. So
Yes.
this is
His work is necessary for proving some things about complete N-representability that I hope Nick maybe will talk about. No?
Yeah, the Helton provided proof that Hermitian sum of squares are sufficient for representing Hamiltonians.
okay.
So in the commutative case, for continuous variables, we know that's not true. That's like Hilbert's 17th problem, where you have to use rational functions. But for finite-sized systems of non-commutative variables, thanks to Helton, we know a solution exists.
Okay, so my instinct wasn't wrong.
Yes.
This is why I invited Nick to this workshop, so that he could answer questions for me. OK. All right, so this problem is going to become very nasty, but I'll spare you the nasty version by giving you a really sleazy level 2 hierarchy based on a spin-free G2. So here, my solution is going to have alpha and beta. Now I've introduced a spin label, sigma. I'm going to have alpha and beta spin 1 RDMs. And I'm going to have a G matrix that involves just these spin-summed generators. And now G, again, I'm going to have 1 in the algebra. So G, again, is going to have these pieces that look like D, that are the top row and leftmost column. OK, and the constraints here, I have a trace constraint. And I've got 2 different linear constraints that map G and D to each other because of this structure. And now, I already showed you from the last slide that we know how to deal with constraints like this. If I have a term that doesn't look SOS, I can always just use my algebra to push it to the right place. And then check my constants at the end to make sure that I did it correctly. What about these parts involving G2? In general, these could be very nasty to deal with, because you can't just, the algebra is more complicated. I can't just, I can decompose G and move things to 2 different sides. It's more complicated. But this case ends up being really simple. And OK, so if I write down my SOS in this way, I have the part that depends on B. I have the part that depends on the constraints. And I have the part that depends on the constants. My trace constraint. And then these are those funny constraints that relate the slices of the G matrix to D1. And I've written them in this silly way with a unit operator. So you know that this part corresponds to an operator on that G matrix. And this corresponds to an operator just on D. But really, this is just a 1. So these 2 constraints actually vanish trivially. So they shouldn't contribute to my SOS at all. That seems convenient. And then, yeah, that's it. That's all we're left with. And this turns out, if I move this trace constraint to the whole space, then I end up having an SOS. And we're done. That's the end of it. So in general, there's a prescription to figure out what the SOS Hamiltonian is from the solution to the V2RDM problem. OK, now I'm going to skip a million slides because I have used all of my time, I think. I have 6 minutes left, but there's way more than 6 minutes worth of slides. If you want to talk about pure state versus unstable state N-representability, we can do that in the break. OK, so to summarize, this V2RDM approach is pretty neat. It gives you a polynomially scaling approach to strong correlation problems, but it has some very serious issues that have yet to be resolved. And it turns out, which I didn't realize until very recently, this is essentially identical to this SOS problem. From that point of view, for me, it's very easy to see that the V2RDM energy is a rigorous lower bound. For quadratic Hamiltonians, it's trivial to extract the SOS from the dual of the primal problem, if you're careful. For quartic Hamiltonians, the algebra gets messy, but it should still be possible. And then why should we care about any of this? Why would I want to extract an SOS Hamiltonian from a primal V2RDM problem? Well, the primal problem is sometimes more efficient to solve than the dual problem, so that's the preferable one to solve. And it turns out there's applications very recently on arXiv from Nicholas Rubin, who's sitting right here, that demonstrate that this SOS structure is very useful in the context of quantum computing, quantum phase estimation, and that's what he'll be talking about tomorrow. So with that, I'll just acknowledge the people in my group, and if you're interested in any of the software, this is our SDP library if anyone wants to play around with it. It's all on GitHub. So, thank you.